Hey there, we're going to go through speeds and feeds and cutting tools and get you set up to start thinking about your machining life here. Um, in this lesson, we're going to identify common cutting tools, learn the definition of speeds, feeds, and calculate the cutting speeds and feed rates for different scenarios. Isn't that exciting? Let's go back here. We've got a center cutting end mill, a ball end mill, a non-center cutting end mill, and an indexable shell mill. Let's start over here with this big one. This has 1, 2, 3, 4, it looks like, spots to insert little cutting blades. Once the blades wear out, you're able to remove them and put new blades in. These guys are more like drills, except they're called mills. So take the DR, kick that out, insert an M, and you've got a mill. What a mill does is it cuts on the side, and these are razor sharp edges called flutes that come down, and they just cut through your material and chuck it into the air, right? This one's center cutting, which means it can drill down into a piece of material similar to a normal drill bit that you might be used to. And this one is non-center cutting, so it's got a little pit right there, and it's really good for going around the outsides or insides, but not so much for going straight down into some material. This one here in the middle's got a rounded top, so it gives you a U-shaped channel when it's all done doing its business, and it can also give you some nice rounded edges and things. If you imagine like what results from this center cutting and non-center cutting end mill, you get a squared out channel, where this one gives you a U-shaped channel. Then you've got some other tools like a combination drill and countersink. So that will drill a hole. It will also give you the flanged opening for hardware, similar to like wood screws. Spot drilling. This is pretty much a drill bit that can go around and give you precision drilled holes at locations that you specify just by putting points into a CAD file. Then you have a countersink bit. These are typically used for things like engraving. 2 flutes versus 4 flute end mills. 4 flutes give you more cutting edges and a longer tool life. 2 flutes give you more room for chips to come flying out of the channels. 2 flutes are typically used for light applications, light metals, woods, things like that. They have a shorter tool life. 4 flutes are for harder materials like metals and steels, and clogs easily with deep cuts. Just for your reference, in our school we don't cut too deep. I mean, we use multiple passes to get deep. Center versus non-center, as I talked about a minute ago, you don't want to plunge directly straight down into material using a non-center cutting mill. You would maybe approach it with what's called ramping, where you come down at an angle rather than 90 degrees to your surface. Here's a bunch of different milling tools. These two are very similar, only this one is a end mill, so it's got that squared off end. This one's a ball end mill, so it's got that round end. Otherwise, everything's the same. They're both 1/4 inch in diameter. They're both 2 flutes. They both have a 3/8 inch shank back here, and they both have this one's got 1 3/4, and this one's a 1 1/4 cutting length. So the cutting length is the distance from the tip to where the flutes kind of stop, right? That shank diameter is really important because you got to hold that tool with the machine, and so you have different collets. That's spelled C-O-L-L-E-T-T, I believe, and that's the part that holds on to the tool back here. We've got probably 4 different collets at the school for our shop bot, and I think our other mill, the high-tech Roland one, the tools already are inserted into collets. So here you've got a 1/4 inch countersink. It's really great for engraving, and the combined countersink and drill for spot drilling and engraving. Facing is when you remove like the top surface of a material. Profiling is when you go around and you make kind of like a two-dimensional path. It's hard to explain. Pocketing is when you make a two-dimensional path, but it's inside the material. So think like the inside of a box. If you were to make a box out of a solid piece, you would make a big pocket, and that would be the inside of your box. Slotting is like making a cut that's good for hardware, for like brackets and things. Roughing is like removing as much of the material as fast as possible, and then finishing is like going back over and making things fine and smooth and ready to use. Okay. All right. And here's a spot drill. The cutting speed is the rate of a tool measured in surface feet per minute. Spindle speed is the number of revolutions per minute that is made by the cutting tool of a machine. And the feed is the distance advanced by the cutting tool along the length of the work for every revolution of the spindle. Cutting speed is the rate of a tool measured in surface feet per minute. Spindle speeds formula. Here we go. This is the good stuff. N is the spindle speed in RPMs. CS is the cutting speed in surface per minute. D is the diameter in inches per revolution. Okay? Surface feet per minute. And so for magnesium, you're going 300 surface feet per minute. Aluminum is 250 surface feet per minute. And you notice it says double the speed for carbide cutting tools. Wow. So carbide can be run a lot faster. What spindle speed should be used to mill aluminum with a 1/2-inch end mill? So you find that data on the chart. 250 is our CS for this one, and everything else is pretty good to go. We've got 250 times 12 divided by pi times 0.5, 1/2 inch. It gives you 1910, right? What spindle speed should be used to mill brass with a 1/4-inch end mill? Well, you've got 150 times 12 divided by pi times 0.25, and that gives you 2293 RPM. So you're using this data and these reference charts to tell the machine how fast you want that spindle to spin. What spindle speed should be used? Okay, we just did this one. Boom, 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 boom. All right. Feed rate is a little different. That's how fast you're moving through the material. Okay, and so you have that in inches per minute, and then you have inches per tooth times your revolutions, and then NT is the number of teeth. And then you might have to calculate the spindle speed ahead of time. Okay, so here we go. We've got face mill, side mill, end mill. They all are similar but different depending on your material. Calculate the feed rate for end milling aluminum with a 2-flute, 1/2-inch, high-strength steel end mill. Well, I think the first thing we're going to need to do is find out that N value. So we've got the FT is 0.005 inches per tooth times revolution. And the N value is that 1910. So we should be able to pump all this in. We've got 0.005 inches per tooth per revolution times 2 teeth. So that's going to cancel out the teeth, times 1910 revolutions per minute. That's going to cancel out the revolutions, which will leave you with inches per minute. And you get 19.1 inches per minute. Calculate the feed rate for face milling aluminum with a 4-flute, 1/2-inch high-strength steel end mill. Boom. Well, aluminum is 250 CS. Okay. And so we'll find out that it is 1911 RPMs. And the face milling business, we've got the 0.005, but this time we have 4 teeth times 19 RPM. And that lets us feed a 4-flute mill through aluminum at 38.2, which is exactly twice as fast as the other one. the 2 flute. Now, should you just be able to double everything for 2 flutes? I don't think so. Here's some factors that affect your feed rates. The power of your motor, your spindle motor. I think the one on the ShopBot is 2 or 3 horsepower, so it's not huge. If you want to go through harder stuff, you got to spin harder. I don't know, more torque. The condition of the cutting tool. Are your tools fresh and new? Are they old and dull? That's going to affect your feed rate. The depth of cut. Are you going 2/10 of an inch down like we recommend at the high school, or are you trying to get 3/4 of an inch all at once? Okay, so it would be great if we could just go as deep as we want and then start cutting to the side, but it makes a lot more sense to just do little bits at a time with more passes. The quality of surface finish required. Do you need it to be great, or can it be kind of not great? Roughing versus finish cuts. Same kind of idea there. Are you just removing as much material as possible, or are you trying to give you the finished result that you desire? The condition of the machine. Is the machine new, or is the machine does the machine need some understanding, right? And the strength of the fixture. Now, fixing your materials down is a whole nother ball of wax. It's a science in and of itself, and so how you're locking your materials in place while you're machining them could affect your feed rate. You don't want that piece to go flying or come loose. That would be devastating. All right, the plunge feed rate is how fast you can go like straight down into your material. And basically you take your feed rate and you divide it by 2. Okay, so here we go. We've got a bunch of different charts with the milling speeds, cutting speeds, tool feed, and how to calculate the plunge rate. There's other operations like tapping, countersinking, counterboring, and this is just for your reference to go back and just make sense of all these different alphabet soup. The trickiest one for me is the CS cutting speed in feet per minute. And check this out. The distance that a point on the circumference of a tool travels each minute. So let's say it spins around once and that circumference is 1 inch. Well, let's say you do 12 of those, then you're at 1 foot per minute, and it just gets kind of off the chain, right? This guy down here, the FT, the feed, is also referred to as the chip load. And so if you hear people talking about chip load, they're talking about the feed, how fast your tool is moving through your material. Okay, so that's the end of this. And yeah, we should be good to go. If I could somehow